Hello and welcome to Chapter 5 of Statistics. So today we're going to start down our path of how can I figure out how likely it is that something happens, or how unlikely is it that it happens? And that's really the adventure of probability. That's going to take us 3 chapters to complete. So we're going to start with what is randomness and what is probability in Chapter 5. In Chapter 6 we're going to investigate some what are called probability models that are discrete. And then in Chapter 7 we're going to be looking at continuous probability models. So that's where we're headed. And once we have continuous probability models and discrete probability models, we'll be able to advance on to our last topic, which is inference. And I'll give you an introduction to inference in a little bit. So what is random phenomenon? It's something that you can't predict the outcome of or how often it occurs, but you know what the characteristics are of it. So for instance, you know that when you flip a coin, there are 2 options, either having a heads or a tails. But when you go to flip the coin, you can't predict exactly what result you're going to get. It's random. Despite being random, you also know that the result is, fairly consistent. In the long run, you should expect to get half heads, half tails, provided that your coin is fair. So the example I just given, each time I flip the coin is what's called a trial. And each time I did that flip, I get a specific outcome, either a head or a tail. And if I want to group outcomes together, these are called events. So heads and tails isn't a good example for events. If you had something like rolling a 6-sided dice, an event might be rolling an even, so there's a couple different options for outcomes, and you group them together into a single unit called an event. The collection of all possible outcomes is called a sample space. So in using that 6-sided dice example, it would be a 1, a 2, a 3, a 4, a 5, or a 6. We usually denote the sample space with an S or an omega, as you see here. And then we're going to calculate what's called probability, which is the long-run frequency of an event relatively. So again, relative frequency, that's comparing the number of ways something can happen to the total number of ways. We've done relative frequency before, but it's been a while. The last thing we're going to talk about, the other important characteristic we're going to run across when it comes to events is the idea of independence. So 2 outcomes are considered independent if one or the other doesn't influence the outcome of another. So the example I usually use for this that physically makes sense is, imagine someone is sitting next to you and we're going to look at the outcome of your blood pressure score, whatever it happens to be. Knowing your blood pressure isn't going to change the blood pressure of the person next to you. So knowing information about one score doesn't indicate what the other score is going to be or change it. So that would be 2 outcomes that are independent of each other. All right. One of the larger information pieces that we get from this is what's called the law of large numbers. There are a couple different laws of large numbers. We're in particular talking about the strong law. And that's the idea is that if you have independent events and you increase the number of trials, then the long run relative frequency of an event gets closer and closer to a single value. This is the idea that if I flipped a coin and I kept flipping, eventually my number of heads would approach 50%. Because about half the outcomes should be a heads, half should be a tails. Anyway. The empirical probability is the number you get based on this. So like I said, getting a head would be 1/2 or 50% or 0.5 is how we're going to use it. We're going to use probabilities. And it's empirical because you did trials to get it. You actually physically went out and did it to calculate it, which is different from doing theoretical probability, which we're going to talk about. So don't confuse the large of law number with the large of averages. The law of averages says that whatever the average is, it must occur in the long run, which does not make a whole lot of sense. This is really also, it's also called the, what's the other name for this? Oh, the gambler's folly. So this is the idea that something that hasn't happened must be more likely to happen. It's again called gambler's folly. And this is the idea that, the object I'm dealing with must have memory. It remembers where it's been, and then therefore it must come up with something else. So like thinking about flipping a coin, if you flipped it 3 times and you got 3 heads in a row, a gambler or somebody who believes in the law of averages says, oh, well, it's more likely that you're going to get a tail on your next flip because it's been heads. That assumes that that coin remembers where it has been and has to make sure that it comes up, an even number of times. And I don't know about you guys, but I'm pretty sure a coin has no brain. So This is an incredibly falsific idea because it doesn't remember where it's been. It's going to randomly produce its outcome. It doesn't care what you've observed or what you remember, because it does not remember it. It is equally likely at every chance to behave the exact same way. So 50% heads, 50% tails, because it doesn't remember where it's been. Anyway, so be careful. The law of large numbers says that over time you'll reach 50% if you keep going and keep trying. Whereas the law of averages is, well, it's just nonsense. Don't try to use it. Okay, so the theoretical model of probability would be that I look at the number of outcomes that are possible for an event that I'm interested in, and then divide it by all the possible outcomes. So as you're looking at this, we read this first statement as the probability of A. So it's of, not multiply. Please don't mistake in function notation for multiplication. If this was multiplication, we wouldn't bother writing the parentheses because there's not more than one thing happening within the A. So the only time you really use parentheses if you have more than one operation. Here we have one operation. You would assume it's multiplication, but that makes no sense. So we wouldn't need parentheses. The operation here isn't multiplication, it's of its function notation. Be careful. So, for instance, if you want to know, hey, what's the probability that I get a 1 on my dice face, that would be, well, there's one way to get a 1 out of 6 options. So there's a theoretical probability for you. This isn't the same as rolling a dice 6 times and counting how many 1s you get. That would be empirical. All right, so here is a little bit of an example. This is from the Pew Research Society again. They asked 10,190 randomly generated working phone numbers to see how many calls were actually answered. So think about this as like, oh, we did this many calls and we saw we got no answer. Busy answering machine called back. They called back to the number if they didn't answer. Other non-contact. So be thinking like you accidentally called a fax line or a number that no longer existed. And then the actual people they got through to. So there you go. So since the phone numbers were generated randomly, each was equally likely. So each is a possible outcome from a random event. And they're independent. And the probability that you get a contact is simply the contact numbers, which would be the 7,400 people, out of the 10,190 that they called. So about 72.67% or 0.7262. This is what a probability looks like. All right. So rule number 1, if I'm counting the number of events out of all the possible events, the number of events is either less than or equal to the total possibility of outcomes of events, which would be the sample space, which would be 1. So the idea is that, well, I can't have a negative number of events, so it's got to be at least 0. Yeah, I could have nothing occur. That would be 0. I can't get a negative, and I can only get positive values, and I could at most get everything, which when I divide something by itself, you get 1. So as you look at this, the number of possibilities is that it's between 0 and 1. So if you are calculating something and you get like a 2.76, that is not a probability, and it is not possible. So keep that in mind when you are writing your answers, because there are going to be things that I will see you do in the future where you will write an answer for probability, and I will immediately know it is incorrect because it's not between 0 and 1. Can't get a negative, can't get something bigger than 1. One of the more frequent things that I see when people are interacting with probabilities is they feel the need to represent them as percentages, and I think this is because of the weather. Not that I'm blaming every meteorologist for every math misconception we have in the world. It's for some reason people like to use percentages when describing something, like I'm 90% sure that it's going to rain tomorrow, things like that, when they should be using a probability for that. They should be saying 0.9 sure that there is, rain happening tomorrow. It's one of those things where semantics has affected the mathematics. So if you're going to represent your probability as being a percentage, then your availability is from 0% to 100%, and you can't be over 100% because it's the likelihood of an event, which is why when I used to watch daytime TV, I got really upset when people would be 400% sure that that wasn't their baby, because you can't be that sure. It is impossible when it comes to probability of an event. If you're not talking about probability, like you're talking about increase in prices or decrease in salary or something like that, yeah, you can use percentages that are over 100. But when you're talking about likelihood of an event, not over 100. Literally impossible. Just so you know. Well, now you know. Anyway, so when it comes to looking at all possible events, and we'd already talked about this, that's everything that could happen. It has to add up to be 100%. So when you're looking at a probability assignment for an event or all the outcomes for an event, it has to add up to 1. Everything must be accounted for. We must make it to 100%. Otherwise, you're missing something. You're missing an outcome somewhere, since the sample space must be all possible outcomes. All right, so if you're not the event you're interested in, aka you're a complement, then you are the opposite of that event occurring. So say you didn't want to roll a 1. So I'm going back to, this idea. So I'm just going to write this 2, 3, 4, rather than drawing the dice heads, sorry, 6, which is the same as, oh, I don't want a 1. Why am I writing this one as a dot then? I don't know what I'm doing. This is the complement of the event before, so that would be 1 minus 1/6, or 5/6, because we like fractions. This is another way to do something. I would advise you to put hearts and stars and little circles and things around the complement rule. In general, when you encounter a probability and it seems difficult, it is almost always easier to do it by a complement. Complements are sort of like, I don't know, the superhero of probability, because they tend to make things easier to calculate. So when in doubt, if you're working on your homework and you feel like you're stuck on something, can't get it to work, and you're not sure why or what's going wrong, try doing a complement. Usually it saves you. Ask yourself, what's the opposite? If I can figure out the opposite, then I can subtract it from 1 and I've got the thing I'm interested in. All right, so here's an example for you. Lee's Lighting sells lighting fixtures. Lee records the behavior, I need to change the name of this, it's too many L's, of 1,000 customers entering the store in 1 week. Of those, 300 make purchases. What's the probability that a customer does not make a purchase? So the first thing you do is you find the probability of a purchase, and that's 300 out of 1,000, or 0.3. And then so the complement, or no purchase, would be just 1 minus the event of making a purchase. So 1 minus 0.3, which would be 0.7. Simple enough. Alrighty. The next thing we're going to look at is what's called the multiplication rule, and I cannot stress this enough. This only works if you have 2 events that are independent. If you don't know that they're independent, do not use this rule. I see lots of people using it all the time and thinking that you can just use it willy-nilly. Don't. Be careful. If you don't know things are independent, do not use this rule. Okay? So here's an example using Lee's lighting fixtures, and we're going to use the multiplication rule because we think that 2 customers and whether or not they will purchase something is independent. So if we assume the customers behave independently, what is the probability the next 2 customers entering the store will both make a purchase? So I've written this out in gory detail on how you can figure this out. So the event I'm really interested in is first customer makes a purchase and second customer makes a purchase. And that's what really makes this, the fact that this is an and. Since it's an and, I can separate it into 2 probabilities times each other, and because they're independent. So that would be a probability of a purchase times the probability of a purchase, which is just 0.3 times 0.3, or 0.09. So about 9% of the time you'll get 2 purchases in a row. The addition rule. This is where you also need to be careful. 2 events are disjoint or mutually exclusive if they have no events in common. The addition rule allows us to add the probabilities of disjoint events to get probabilities that either event occurs. Okay, so be careful. If you don't know that things are disjoint or mutually exclusive, you cannot use this rule. So this is the same warning with the multiplication rule. Be careful. If you don't have disjointedness, you should not be using this. So if you look at things that are overlapping, you should not be using this addition rule. This is actually not the most general addition rule. There's another one we're going to do in a minute that is actually a little bit better. So here's the idea. If I know that these 2 share nothing in common, then I can just add their probabilities together. So it would be like for our dice looking at, oh, I want to do the probability that a number is even plus the probability that a number is odd. They share nothing in common. I can totally do that. If they share anything in common, you can't do that. Beware. Be careful. Don't do crazy stuff. Okay, so here's an example. Some customers prefer to see the merchandise, but make their purchases online. I don't know if y'all have ever done this before. Lee determined that there's an 8% chance that customers make a purchase in this way. So we know about 30% of customers make their purchases when they enter the store. And what's the probability that the customer who enters the store and makes no purchase at all? So this is the idea that the purchase is either in store or online. So if they purchase in store plus the purchase online, because you're assuming they do not do both. So a person that purchases in the store is not going to also purchase it online. Vice versa is also true. A person that purchases online is not going to be purchasing in store. And then you can just add their probabilities together. The 0.3 plus the 0.0. That should be 0.08 for purchase online. That's a typo. I'm sorry, I just caught that. My bad. Okay, and that means that when I go to make no purchase, then this would be 0.38, and therefore this is 0.62. My apologies. I'll have to fix that for next year. So the idea being that, oh, well, the only reason I can do these is because there's no overlap between them. So if there was a probability that you could purchase online and in store and you could do both, then you wouldn't be able to use this and rule of just adding them together. Then you should use this rule. This is called the general addition rule. And so the idea is that how do I find the probability that A or B happened? Well, I take the probability of A plus the probability of B and I subtract the overlap. Okay, let me give you an example of this. So let's say you want to find the probability that a person in your class is left-handed or has green eyes. I should have picked a easier to type draw word things. Anyway, so then what are you going to do? Well, I'm going to take the probability that a person is left-handed, add together the probability that a person has green eyes, and I should be good, right? No. Here's where the problem arises, okay? Do you know anybody who's left-handed and has green eyes? Then they're in both of these. Okay, so that person got counted here and here. You overcounted anybody who was in both. Anybody who had both a left hand and green eyes. Anybody who is left-handed, not has a left hand. I hope you all have left hands. Here's a horrible stats joke for you. The average number of legs in the world is less than 2. Oh, sorry, that a person has. That's horrible. Why did I tell you that? Okay, so what happens? Okay, because there are people that have both characteristics, aka and, I've double counted those individuals, so I subtract the and characteristics, left and green, to account for that double counting. So I got rid of the overcounting. Let's look at another example. So Lee notices that when two customers enter the store together, their purchases are not disjoint. So if you showed up with your best friend, if one of you bought something, more likely is that the other person would buy something as well. That happens about 20% of the time. So this isn't disjoint. So in fact, there's a 20% chance that they'll both make a purchase. When a customer enters the store, what is the probability that at least one of them makes a purchase? So now I'm looking at least one purchase, which is the same thing as person A, or the first person purchases, or person B purchases. So one or the other. So that would be the same as looking at A purchases, B purchases, or both of them makes a purchase. So I have to be careful because I've overcounted both. Yeah, so groups of twos that enter together, if one of them makes a purchase, the other is more likely to. That happens about 20% of the time, in which case you've overcounted those groups because they show up in both A and B, so I need to subtract them. So that would be 0.3 plus 0.3. That should have been an equal sign. That looks lovely. 0.3 plus 0.3 minus the overlap, and that gives you 0.4. This is much more common, okay? Usually independence is a little bit harder to come by. You should expect to use this rule over the other rule, okay? That's why it's called the general one. You know, it's like the one who will lead you into battle. That's not really what it means. Okay. Let's get our cars inspected for fun. You and a friend are going to get your cars inspected. The event that your car has a passing inspection is independent of your friend's car because your cars are different, assumingly. Unless you both buy the same car, which my husband totally did, and his best friend, and I thought that was super weird. Anyway, about 75% of cars pass inspection. Hey, let's find the probability of some different events. What's the probability that your car passes inspection? What's the probability that it doesn't pass? What's the probability that both cars pass? What's the probability that at least one of the two cars passes? What's the probability that neither car passes? Ooh, you should be thinking about, ooh, there's some knots showing up in here. Yeah, right here and right here. Not and neither. That's usually a good indication that I'm going to be using a complement somewhere. Oh yeah, it could happen. Let's do this. So the first thing we're going to look at is the car passes. So just one car. So that would be 0.75 as is described previously. There are questions like this on your homework that are that easy, so don't overthink it, okay? The probability that you don't pass inspection, that's a complement. So notice there's that little C, pass, complement, or fail. And that's 1 minus the 0.75 because we already found the event that you passed. So then we move on to what's the probability that both cars pass inspection. Now, we've already decided that your cars are independent of each other. Because of that, I can use the multiplication rule. So you're going to do 0.75 times 0.75, and that'll give you 0.625. So that's a pass-pass. Now we're looking at, hey, what's the probability that at least two cars passes? At least one of the two cars passes. Okay. So I want you to think about it this way. Your options for this are, oh, we both pass. Okay, my car passes, your car fails. You know, my car fails, your car passes. Yeah, you could do it that way. At least one car passes. That's the scenarios for this. Or you could look at them and be like, no, this is the opposite of we both fail. Yeah, that's the only event that wasn't included, which is exactly what we did here. We did a complement. So it's the opposite of we both fail. At least one of them passes. Cool. Yep. And that's where we come up with the 375. And then lastly, look at neither car passes inspection. Oh, well, that's the complement of the previous event. At least one of them passes, or none of them passes. So I can just do the complement again to arrive at the none of them passes. Or you could just do fail, fail, which would be this guy. Those are the same. So if you don't believe me that those end up being the same, take a minute to ask yourself, oh, is the probability that both fail the same as what I just claimed, 1 minus the at least one passes? And you can calculate that and check to make sure. That is also one of the things that's, what's the word I'm looking for? Different about probability. It's a lot like algebra in the respect that there are lots of ways to do things. Just because I do it one way and you do it another doesn't mean you're wrong, okay? So if you wanted to try something else, like the scenario I gave you at the beginning, like I want to do pass, pass, and then pass, fail, and then fail, pass, and calculate all those and add them together, more power to you. It's still going to come up with the same answer. The thing you need to be careful about is don't round, okay? And make sure you don't miss any events. As long as you abide by those two rules, you should be pretty good and come up with the same answer. So when you're looking at your results for some of the examples I go through in the example videos, just look at your answer versus my answers. If they're the same, you're good. If not, you might want to actually look at how I did something to see if your method was still valid and just maybe you made a mistake or two. Alrighty, let's talk about contingency tables. You've seen these before. They're also called two-way tables. Does that look familiar? We've already done this. So welcome to the day of deja vu, or sorry, not the day of deja vu, the moment of deja vu in our stats class, because we're going to go back over some probabilities that we've already talked about so that you're aware of how we actually could use those. So in previous, sorry, which chapter was this? Chapter 2, we talked about how to use two-way tables to calculate some counts and do relative frequencies. Those were actually probabilities, because as earlier we discussed, probabilities are just relative frequencies. So below I have an example where you are picking a prize for a promotion, and you choose which of the 3 prizes you'd like to win, and they separated that by gender. So I've got 2 variables interacting, sex and prize preference. Whew, sorry. And I've got the totals on the margins along with the total of totals. This is not a new idea. As you recall, margins are called marginal distributions, and probabilities that use the margins are what's called marginal probabilities. Let's do one. So if you want to look at what's the probability that an individual is a woman, you would take the total for all women, notice it's on the margin, and divide it by the total of totals. Yay! So what makes something a marginal probability? When it only involves things on the margin. There you go. Let's do another. Let's look at a joint probability. So joint probabilities involve anything that's in the middle of the table that is not marginal, and the total of totals. These are all going to be ands. They will hold both two characteristics from each category. These are always ands. So joint, I join you together, and ye shall be together for forever. I don't know why this sounds biblical to me. Woman and camera? 91 out of 478. Okay, so I'm hoping you notice that joints tend to come from the middle of the table and they represent ands. So when I look at this group right here, these 91 ladies, these 91 individuals, they represent two characteristics. The characteristic of being a woman and that's the most important part, it's an and, they want the camera for their prize. And that's the big thing. Joints are ands because they come from two characteristics in the center of the table, not the edges. The edges are just like no ands and stuffs. Okay. Let's look at the last idea, what's known as a conditional probability. This is the one we've done already before, but we didn't call it this before. All right, looking at the table, what is the probability that a selected customer wants a bike given that we already know that individual is a woman? So amongst the women, how many of them want a bike? So I'm looking at using a marginal for our total, and I'm looking at a joint to make our numerator. Amongst only the women, what's the probability that they want a bike? That's what a given or conditional probability is. So the big thing that's going to cue you into doing a conditional is I'm shorting up my number of individuals in my total, and I'm looking at the conditional distribution. Ah, yes, I'm only looking at one row or one column and considering its values, not the entire table. So I'm not using the total of totals, I'm using a total off of one row or one column. Alrighty. Here's how you write that using mathematics. This is called a conditional. So we read this as the probability of B given A. The idea is that, oh, I already know A happened. What should we do to calculate B? Like our previous example is, oh, I already know it's a woman that I've selected. What's the probability she selects a bike? So I know a little bit more information. Conditionals should always look different than regular joint or marginal probabilities because they're on the condition that you already know something. Yep. So here's how that looks. Hey, what's the probability that B happened given that A already happened? So when I look at the probability of B happening, it's B and A because, well, I already know A happened. And I'm counting that only out of the individuals in A because, well, I'm only looking at A because I know A happened. This seems to make a lot of sense. Let's look at the probability we just did using the conditional probability that we calculated where that was a conditional. If I would have done it with the formula, they come out exactly the same. Oops. Okay, so I totally shouldn't be here. I should be back on the previous slide. This is so annoying. Anyway, if you rearrange that formula, you get this. So if you took in the previous formula and solved for A, I'm sorry that my slides are out of order. The one I'm about to do in like a second should be sooner. So if you take the formula for conditional probability and solve for P of A and B, you get this formula. This one doesn't come up that much, but hey, you know, there you go. There it is. Woohoo. Let's go on to the example I meant to be right here. That was 30 seconds of me saying nonsense. Anyway, so if we did this using the formula, this is what this would look like. So we're looking at, you know, probability of bike, given that it's a woman. So in the numerator, I have bike and woman, which we calculated earlier, or we can calculate right now. That's 30, bike and woman, out of 475. And then the probability you have a woman, that's one we did earlier, 251 out of 475. I'm hoping you notice that this is the same as 30 out of 251, which is how we had done this earlier, or 0.12. It comes out exactly the same. So you don't necessarily have to use the formula to do this, but sometimes it is easier to use that formula to do it. So why do we bother with conditionals? You should be looking at this and be like, okay, we've done this before, not that interesting. It's because of independence. So if two events are independent, whenever I look at the conditional, like the probability of B given A already happened, it comes out exactly as just the probability of B. And this physically makes sense because it's saying to you, oh my gosh, well, if I know A, did I really change the probability of knowing B happened? Nope, because they're independent. It would be just like asking you, hey, is it going to rain tomorrow? And then I'm like, but wait, it's going to rain today. Does it really change anything? No, it doesn't. I mean, usually those two are independent of each other. So this is also a good way to check for independence. The idea that, oh, if I know A, it doesn't impact or change anything, and therefore knowing anything about A doesn't change what B looks like. Yay. Let's see this in action. So I'm back to gender and bicycle preference. And sorry, sex and prize preference. Sorry, I knew it was a bike, and so I was saying bicycle. I apologize. So if you look at this again, I'm like, oh, I just found the probability that bike, given I know it's a woman, would that be the same as just bike? Because if they're the same, then I know the probability of selecting bikes for that gender are independent of each other. So I would say that sex and prize preference are independent. They have no relationship to each other. So you look at this and you calculate the probability of bike, and I'm using the probability we calculated a couple slides ago for bike given woman. And it comes out, oh, well, the probability of getting a bike is like 0.265. Oh my gosh, these two aren't equal. That means, hey, you know what? These are not independent. It appears that gender and prize preference are related. And so I should expect that if I know the gender of an individual, which prize they're more likely to select. Fun times. An important thing to note about this is that independence and disjointness are absolutely not related. Knowing that something is disjoint doesn't tell you if it's independent. Knowing that something is independent doesn't tell you if it's disjoint, so be careful. Just because you can use the multiplication rule doesn't mean you can use the addition rule. Be careful. The only way to really check independence well is something that you learn in Stats 2, and that is called the chi-squared test. Other than the conditional we just did, that is the only other way you're going to be able to do it. So don't assume independence. Don't assume disjointness. Just as a reminder, these are the formulas I was just talking about. Hey, here's how I can check independence or disjointness. The only way for disjoint is, hey, these don't overlap or share anything. They can't occur at the same time or can't occur together. So you can't be both. I was about to say you can't be both left and right-handed, but you totally can. That's called ambidextrous. You can't. What's one you can't both be doing? I was about to say you can't be both single and divorced, but I think you can. Wait, no, you can be both single and divorced. You can't be both married and divorced unless you're a bigamist, in which case, oh, no, wait, that's another one that doesn't work. Dang it. Okay. I'm pretty sure you can't be two species. You can't be both a human and a lizard. There you go. Done. I'm really struggling to find a good disjoint example. Ah, got it. So picture a pack of cards. You know the suits that they have are hearts, diamonds, spades, and clubs. You can't be both a red card, aka a heart or a diamond, and a black card, which would be a spade or a club. There you go. There's some things that are disjoint. You can't be both of those. Okay. Independent. Independence is not the same as disjoint. You should be checking one of these three to determine independence. And when I say checking, there's equal signs here. So that means you should be checking, are these two equal? Are these two equal? Are these two equal? One of these, whichever is the easiest to calculate. Okay? And if they're not independent. That's the idea. You don't know that they're equal unless you know that they're independent. So be careful. I've blathered on about this. It is super important coming up, so, you know, there's that. It's going to feel less. Come on. It's going to feel less important in Chapter 7. Anyway, it'll come up still, though, if you're watching for it. So if you're given a probability without a contingency table, you can often construct a simple table of correspondence and probabilities and use this to find the table and or other probabilities you might want to know. So the idea being that if you're missing something, you can fill in the gaps. So here we go. So a survey of homes in two price categories, low and high, also noted that the house had at least two bathrooms, either as a true or false. So if 56% of the houses had at least two bathrooms and 62% of the houses were low price and 22% of the houses are both, we can translate that into the following table. So these are all in probabilities. And now what we want to do is fill in the blanks of what's missing. Okay? So first we note that the 56 and the 62 are marginals, so they go on the margins, and then 22% is a joint, since it's talking about a both or an and. And you know that there's at least two bathrooms, and so what we want to do is we want to come up with the remaining values in this table. And Since the events are disjoint, you can't be both low priced and high priced. We actually can fill those in using what we know. So since the total for this is 56, to find this 34%, I'm just doing 0.56 minus 0.22. And then to find the 0.4 here, I'm doing 0.62 minus 0.22. And then the remaining can be found doing the following. So this is the long and short way to get to 0.04. So I noticed that this is 0.56, but it must total to bank 1, so that is found by subtracting to give you 0.44. And the same thing here for 0.38. And then you can either use this total across the row or total down the column to realize that must be 0.04. So again, this only works if you have disjoints. So I know that you can't be both. Don't try this with anything else. It's rather difficult. It's awful. Anyway. Let's look at another example of constructing a contingency table. A national survey indicates that 30% of adults conduct their banking online. It is also found that 40% are under the age of 50, and 25% are under the age of 50 and conduct their banking online. Fun times. Hey, what's the percentage of adults that do not conduct their banking online? What's the probability? What type of probability is the 25% mentioned above? This is where I get annoyed because it's like probability and then it lists a percent. Those are not the same thing. To do this correctly, it should be 0.25. Because, you know, probabilities aren't percentages. Usually we talk, okay, never mind. Construct a contingency table to show the joint and marginal probabilities. Woohoo! What is the probability an individual who is under the age of 50 conducts banking online? Are banking and online and age independent? So a couple things as I look at this, and I meant to warn you about this earlier, but now I'm doing it now. When you look at percentages and you see the word percent, you should be answering in percent, which means that when you're reading things and answering questions on your homework, be careful. Watch for the word percent. It's going to come up a lot, and when it does, you should be listing a percentage, not a probability. If it doesn't say percent or use the percent symbol, you should be using probabilities, which are between 0 and 1, aka they should be a decimal. Be careful. You have been warned. Like, warning, look out for percents. That looks like symbolic nonsense. Okay, so what's the percent of adults who not conduct their banking online? This is the complement of the event that an adult conducts banking online, and that would be 100% minus 70%. What proper probability is the 25% mentioned above? That 25% is an and, because, well, it's really a marginal because it's looking at the individuals who are under the age of 50 and conduct their banking online. That's actually incorrect. That shouldn't be a marginal. That's a joint because it's using stuff from, well, it's an and. Done. Okay, so let's fill this out. So there's my 25%. I'm hoping you notice it showing up here because it's an and. There's the 40% and there's the 30%. You fill in the rest of these table values using the same methods we did previously. Good times. Shorter ago. Let's use this to indicate whether or not age and banking are independent. So the first thing I'm going to do is calculate the probability, that an individual is under the age of 50 and conducts banking online. Who is under the age of 50 conducts banking online. So really what I'm doing is I'm calculating the probability of, oh, I wrote it down here. Banking online given that they're under 50. So this is a conditional. And that's right there. And then I want to notice that, oh, that's not just the same as banking online. These two aren't equal at all. So, you know, clearly these are not independent. It appears age is an effector on the whether or not they use online banking. And I want you to all think of somebody you know who's around 50 or 60 or over the age of 50 and ask yourself, have they written a check in the last year? The answer is yes, they probably don't bank online. Fun fact. All right. Let's talk about probability trees. We're going to teach probability trees simply because they're a great tool when it comes to organizing your thoughts. If you do not like these, yes, you can diagram or figure out your probabilities using different methods. Don't feel like you're forced to use these, but because they are so prevalent, we are teaching them. And I want you to be aware of the fact that You probably are going to have to read one at some point in your life, so that's why we're going over this. Anyway, so if you have more than one decision possibly popping up, aka more than one variable interacting with another, sometimes tree diagramming this will help you decide what the probabilities look like and or help you with the decision-making process. Those if you're interested in big data, this also shows up in neural networking and learning systems, which those sound like they should be involved in teaching and learning. They're not. They're about teaching a computer to watch out for certain indicators that show up and then predict behavior based on those indicators. So like the best example I have of this is Target predicting pregnancy and then for sending out prenatal coupons to people, which there's some fun articles about that, in case you care. Anyway, so let's look at an example. A personal electronics device, such as a smartphone or tablet, are getting more capable all the time. Hey, microscopic and even microscopic flaws submicroscopic, can cause intermittent performance failures and develop during their manufacture. Defects will always occur, so a quality engineer, somebody who wants to know how often they get these problems, is in charge of the production process used to monitor the number of defects and take the action based on the process that seem out of control. If you'd like more on control processes, that shows up in chapter 21. So the following is a probability tree that shows the manufacturing problem that occurs, well, where it can occur and whether or not it's fixable. So this is an interesting idea. So anyway, it makes more sense with sheet diagram. So here's what I want you to be thinking. There are three big problem areas for the cause of what can go wrong. Case, like the casing screwed up, the memory screwed up, or the motherboard. And right next to this, we have the probability of each of those. So about 10% of the time, it's the motherboard. Get the idea? And then after that, knowing that it's a motherboard, can I fix it or not? Yeah? Knowing that it's the case or not, can I fix it or not? So if you follow the path down this tree, so it kind of looks like branches if you flip it upwards, or if you flip it downwards, it looks like roots, hence the name tree. You can go across up here and be like, oh, case, and it was fixed. What's that? Well, these two are independent of each other. That's 0.6 times 0.8 because the probabilities are listed there, and you can calculate that, and so on and so forth. So for instance, if you were looking at, oh, what's the probability that something was fixed or is fixable, you could go down the branches that involve fixing and add those all together. So you do 0.3 times 0.5 for this one and add it, and here's a fixed one. So you go down this branchy poo and 0.1 times 0.1, and you would add these three together, and that would give you the probability of, oh, I can fix this. So if you were the quality engineer, you might look at this and be like, oh, hey, what's the probability that I can fix it in general, and where can I improve that would be another option. Like, so I look at this and I notice that, oh, the worst thing in here, or the worst probability for not fixed, appears to be the motherboards, because that's not fixable 90% of the time. Oh, but I only have motherboard issues 10% of the time. So keep in mind, although it's harder to fix, it's not as likely. So it might not be motherboards I should worry about so much. It appears that you have to be, sorry, not that it appears, you have to be aware of not only what's the probability I can fix it, but also what's the probability that it happened. Because if it's not fixable, but it doesn't happen all that often, it might not matter that much. Excuse me. So, for example, each of the branch probabilities are joints and can be calculated by a multiplication rule from the independent events. I already talked about this. There it is with all the multiplication glory. Fun times. So, for instance, like I said, if you wanted to know the probability that something was fixable, you would add these three together and be like, oh, well, it appears, yes, I can fix it about 60, oh no, adding in my head, not going so well, 64% of the time, God, I hope that number's right, it's fixable, which is a pretty good number, I'd say, you know, when an error occurs. Good times. I don't know if you care. The other thing I would look at this is when it's not fixable, it appears that although I suspected case was going to be the worst one, memory seems to be the worst one. So we should work on not making as many memory errors if I was in charge of quantity control. Using probability to make decisions. Good times. All right. Let's go forth. Oh no, it's not going forward. There we go. All right. So when you need to reverse a conditional, aka go from instead of A given B, instead of B given A, we can use what's called Bayes' rule. So there's a whole separate branch of statistics dedicated to how to reverse different processes in statistics, and these are all called Bayesian statistics. So I'm going to show you Bayes' rule. It doesn't come up that often in what we're going to do. I just want you to be aware of it in case you go into some more advanced mathematics in the future and you might need it. So here's Bayes' rule. Good times. So if I have I events for n events and they are mutually exclusive and exhaustive, aka their union is the entire space, so I've accounted for all possibilities. Here's how this comes up. That looks gross, doesn't it? Here's the simple version if you just have two events. So if I have A given B and I want to know it, I can take B given A and multiply it by the things I need to switch it over there, which would be multiply it by A and divide it off by B, because I want to put B into the denominator because, you know, it's given B. That's it. Okay, that's the simplified version. So where this gets complicated is where you have more than two events. So this can get kind of gross quickly, but it does allow you to switch your conditional. So what do I mean by that? Sorry, it's not letting me click on another color. Notice that if I know B given A, it switches it to A given B. So it's just a way of switching your conditional onto a different event. Good times. Let's talk about what we've learned. Sorry for the big sigh. All right, so be careful. Probabilities can't add up to 1, so don't start adding stuff. In general, there's not a lot of times you add probabilities. I'm hoping you notice that. Don't add things that are disjoint. I keep talking about addition because people tend to do it when they shouldn't. Don't multiply probability of events if they're not independent. The most frequent time you're going to show multiplication showing up where is where you have more than one event occurring. If they're not independent, you shouldn't be multiplying them. So think back to the tree example we just did. I have what's the problem and can I fix it? Those are two independent events, and we were able to multiply them together. So I had two things happening, like if I draw two cards from the deck, not one. So if you have multiple events, you multiply. Get the idea? Okay. Don't confuse disjoint with independent. Disjoint is they have nothing in common. Independent is they do not depend on each other when it comes to their probabilities, or knowing the probability of one influences the probability of the other, possibly. Okay, what did we learn? We talked about frequency, and that's what probability actually is. It's the long run frequency, or it could be the theoretical frequency. Probability should be between 0 and 1. The sum of all probabilities should be 1 in total. This is what's called the law of total probability. In case you care, remember the law of averages is just bunky, crazy nonsense, and then the law of large numbers is not. Things approach their average. Ay. So crazy. This is the slide you should put hearts and stars and highlight and maybe, make your own copy of, because it's the one you're going to use the most. It's all of the rules together. Pay particular attention to the general rule of addition and the general rule of multiplication. Those are the ones you can use in general all the time without any additional thoughts or requirements. The problem is that if you want to use the addition rule and not the general addition rule, you have to know that they're disjoint. If you want to use the multiplication rule and not the general multiplication rule, you have to know that they're independent. So be careful. The ones I've starred are preferable to the ones that have underlines, because the ones that have underlines are ones that require additional characteristics. Watch out for this. Okay. All right. Know how to construct and read contingency tables. This is pretty easy once you have your ands and your ors in order. Watch out for marginals versus joints in order to make sure you have these in the right spot. That's the biggest thing with those. Don't assume things are independent. In fact, you should check for independence. See if the conditional matches the non-conditional. If they're the same, you've got some independence action. That's a good thing. Be careful. Make sure you know how to do tree diagrams and how to use them to calculate some probabilities. I know I know how to use Bayes' rule and compute conditional probabilities on here. You're not going to really need to know it. I want you to have seen it and be aware of it should you go forth and need it someday in your future. Almost none of you will.